I just want to talk a little bit about matchings because what we're going to cover is actually very similar to matchings. And we'll see a connection at the very end of this lecture as well. So suppose I give you a graph and I ask you for a maximum matching. Based on the things that we have learned so far, how can you design an algorithm that gives me a maximum matching? Well, I can just start with a trivial matching. Let's say I take the empty matching or I take any maximal matching. And then I know that if this is not a maximum matching, then I can augment it. So I just search for an augmenting path. And if I find an augmenting path, I augment it, I get a bigger matching. And I keep doing this for as long as I can. And eventually I'll get to a matching that cannot be augmented anymore, and that's a maximum matching, right? We're going to see another problem that is solved using a similar technique. So the technique is that you start with a non-optimal solution, and you just keep making your solution better and better. And in this case, we're also going to call it augmenting, until at some point you cannot improve your solution anymore. But then we have a theorem that says when you cannot improve it anymore, it's definitely optimal. Okay. So the problem we're going to look at is called network flow. So this is how this works. Suppose that I have a directed graph, and let's say that every edge also has a capacity. So I have a directed graph G. With vertex set V and edge set E. But I also have a capacity function that maps every edge to some number, let's say between 0 and infinity. Okay, that's the capacity of this particular. And then I also say that I have two particular vertices that I care about. I have a vertex S and a vertex T. These are in my set of vertices, and I call S my source, and T is my sink. Okay. Let me give you an example. Let's say that this is my graph. So I have vertices A, B, C, and D. And let's say I have these edges. Okay. And every edge is going to have some capacity. So let's say this one has capacity 1, this has 4, this has 6, this has 5, this one has 4. Okay. And then I'm going to say one of the vertices is the source. So in this case, I say A is my source. And one of the vertices is the sink. I say D is my sink. Now, the idea is like this. You have to think of it, let's say, like pipes that can carry water. So this means that I have a pipe from A to B that can carry 4 units of water. So let's say 4 liters of water per second. Okay. And I have a pipe from A to C that can carry 5 liters per second, and so on. And now what I want to do is that I want to open a tap at S, at my source, and I want to send all this water to the sink, to this vertex D, right? But I want to have the maximum possible flow. So I want to open the biggest possible tap that I can at the source, such that all the water reaches the sink. Okay, so this is an intuitive definition of what we want to do. This is called the network flow algorithm, in this case, max flow. But let's actually define this. Let's say what a flow can actually mean. So first of all, if I have a capacity, so I have this capacity for every edge. So for example, here I have a capacity of 4. So I cannot send a flow of more than 4 units on this edge. So I have to choose how much flow I want to send on this edge, and I have to choose a number less than 4, less than or equal. Now, to make my life easier, I'm going to say that I don't just assign a capacity to every edge. I actually assign a capacity to every pair of vertices. So the idea is that if I don't have an edge, for example, from A to D, I don't have an edge, then the capacity is 0. Just think of it like that. Okay. So that for every pair of vertices, I can talk about the capacity. Okay. So I want to define what a flow is. So I say a flow is a function, let's say f. And again, the idea is that this function f is supposed to tell me how much water I'm going to send through every edge. So it's going to take an edge and it's going to map it to a real number. Okay. But just like before, I don't like to work with edges. I prefer to work with pairs of vertices. So let's say that my function actually takes two vertices. Okay. So basically, f of uv is the flow from u to v. Now, what are the conditions that I want to be satisfied? So these are the conditions. The first condition is, of course, that I cannot send more flow than the capacity. So I have to have this. I have to say that for every pair of vertices u and v, the flow from u to v is at most the capacity from u to v. Very tricky. The second condition is actually the one that is going to confuse you the most today. And it's this one. It's called the skew symmetry. So skew symmetry says that for every two vertices u and v, the flow from u to v is minus the flow from v to u. Okay. So just to give you some intuition as to what I'm saying here. Whenever I'm sending 2 units of water from A to B, I can think of that as sending minus 2 units of water from B to A. Okay. And this is exactly what I'm doing here. So f of uv is not exactly the amount of flow that I'm sending on this edge. It's like the amount of flow that I'm sending from A to B. But if I'm sending from B to A, it's going to be the negative. Right? So that's the intuition here. So for every pair of vertices u and v, f of uv is minus f of v. Okay. But what I told you was that I'm going to open a tap at the source and I want all the water to go to the sink. So at any other vertex other than the source and the sink, I want to make sure that the amount of water that comes in is equal to the amount of water that goes out. So the inflow should be equal to the outflow, right? How can I write this? This is actually called the preservation of flow. I can say it like this. I can say for every vertex u, so for every vertex u that is in the set of vertices, but is not my source or sink, what do I want? I want the flow coming into u to be the same as the flow going out of u. But I'm going to write it in this way. I'm going to say the sum over all vertices of v of f of uv should be what? 0. So what is this sum? This is basically saying, look at the flow from u to every other vertex, right? But because of the previous condition, if I have a flow from some other vertex to u, it's counted as a negative here. So when I take the sum of all the flows, it should be 0. So this is one of the reasons why I added a skew symmetry, because it makes my life easier. I can write something like this instead of having to say the sum of the flows that come in is equal to the sum of flows that go out, right? This sum already contains everything. And of course, I can also write this in the other direction. I can say the flows from V to U. And this is, again, summing over every V. This should also be. Okay. Again, to just imagine this, suppose that I have this vertex U, and I have, let's say, 2 units coming in from here. I have 3 units coming from here, and I have 5 units going out here. Okay. So what does this mean? This means that, let's give these some names. So let's call this one V1, V2, and V3. So f of u V3 is 5. Okay, but what is f of u v1? It's -2. F of u v2 is -3. So the sum of f of u v is 0, which means that the amount that is coming in is the same as the amount that is going out. Okay, and this one is just saying this in the opposite direction. So f of v1u is 2, f of v2u is 3, f of v3u is -5. Okay, great. So I have these conditions, and whenever I find a function f that satisfies these conditions, I say that f is a flow. Okay, but of course I said that I want to send the maximum possible amount of money, not money, water in every unit of time from the source to the sink, right? I'm not sending money to anyone, just water. So I want to send the maximum amount of water. So I have to somehow define what is the amount of water that this flow is sending. And I actually show that like this. I say that's the amount of the flow. So when I do something like this, this is like the amount of water that is sent from the source to the sink. Okay, but what do I know? I know that for every vertex other than the source and the sink, the sum of the flows out of that vertex is 0. So for the source, the sum of the flow going out is going to be more than the sum of the flow coming in, right? I know it's weird, but I can actually have some flow that goes around and comes back to the source, right? Because these conditions are not really saying that I cannot have any flow back to the source, right? So what is the amount of flow that leaves the source and goes all the way to reach the sink? Well, this is just the sum over all vertices of f of source and v. Again, if I have my source vertex, if I have some flow going out, this flow is counted as positive in this sum. But if I have something coming back into my source, this is counted as negative. So when I just take this sum, it's literally the remaining amount. It's what goes out of the source and never comes back. Okay. And similarly, I can say that this is equal to the total flow that goes into the sink, right? Because everything that goes out of the source has to end up somewhere. It cannot stay anywhere. It has to go to the sink. So basically, if I'm measuring the water, I can measure it here. I can see how much is going out, or I can measure it here, see how much is coming in, and it's going to be the same. You can actually prove that. I'm not going to give you the proof, but it's a very simple proof that these two are the same. Okay, so what is my goal now? My goal is, given a network, which is a directed graph like this with capacities, I want to find the maximum possible flow from the source to the sink. Okay. Let's just try it on this example. And let's see what we can do. Okay. So initially, my flow is 0, of course, because I'm not sending any flow anywhere. So let's say that I want to start and I want to send some flow, not necessarily an optimal amount, from A to D, from my source to my target. Okay. How can I do that? Well, I just need to find a path, right? Or I mean, it doesn't even have to be a path. I can find a walk if I want to, right? And we know how to do that. For example, we've seen the BFS algorithm. Anyway, let's say I find the path. So let's say I look at this path. I've learned how to do dashed lines. I want to use that. So I do this path. Okay. So suppose I want to send some flow along this path. How much flow can I send? 1, right? Because this one, this edge or pipe, has capacity 4. This one has capacity 1. This one has capacity 5. So you can only send the minimum of all the capacities. So I can send 1 unit of flow along here. So let's say that I just write how much flow I've sent in blue. So I send 1 unit of flow here. I send 1 unit of flow here, and I send 1 unit of flow here. Now my total flow from source to sink is 1. Okay. Now I can just continue the same thing. Try to find another walk from your source to your sink. And let's see if you can add some flow. Now, in this case, the answer is no. Or is it? No, it's not no, actually. I can find this walk, right? So I can find this walk. And how much flow can I send here? 4 units, because even though this one has capacity 5, 1 unit of the capacity was already used before. So it has 4 remaining units of capacity. I can send 4 units of flow here. So this one will have a flow of 4. And this one will get a flow of 5. Okay. Can I send any more flow? How? ABD. Okay. So I can send 3 units from here. Okay. But interestingly, I can do something else as well. So I want to show you a different way of sending flow. I can send flow along this path. So I can do this. Why can I do this? I claim that I can send 1 unit of flow along this path, even though it's not even really a path in this graph. Okay. So what does it mean to send a unit of flow along this path? It means that I want to send 1 unit from A to C. And I can do that because I have the capacity here, right? And then I want to send 1 unit from C to B. But I was already sending 1 unit from B to C. I can just cancel that, right? That's equivalent to sending 1 unit of flow from C to B, right? And then I can send 1 unit of flow from B to D. So when I'm finding these paths, I can be creative. Instead of just finding paths in the graph, I can also find some paths that cancel some of my previous decisions because they increase the flow. Okay. So I want to somehow formalize this. And this is what I do. I say, when I draw my graph, I'm now going to draw all of the edges. So I'm also going to draw the edges with capacity 0. Okay. And I'm going to keep track of my flow like that. So let me go back and again copy this graph. So I have this graph. And again, remember that I'm imagining that I have edges between every pair of vertices, but all the edges that I have not drawn here have a capacity of 0. Right? So now, when I first send some flow, when I first send, let's say, 1 unit of flow along this path, what does that mean? This means that I'm sending 1 unit of flow from A to B. So basically, F of AB is 1, right? But by definition, that means that F of BA is -1. Okay, -1. My hand doesn't listen to my mouse. Okay, so I can think of this as having an edge from B to A where the flow is -1. But what is the capacity of this edge? It's 0. Right? But this is fine because -1 is smaller than 0. Right? So my condition here was that the flow on every edge should be less than its capacity. And remember, I intentionally said that I assign capacities not just to edges, but every pair of vertices. So the capacity from B to A was 0. That's why I wasn't even drawing this edge. But now I'm sending a flow of -1 there. So that's fine. I'm happy with that. So similarly, I'm sending a flow of 1 here. So I have an edge in the opposite direction, which has capacity 0 and a flow of -1. And here, again, I'm sending a flow of 1. So I have an edge in the opposite direction, which has a capacity of 0 and a flow of -1. Okay. Now this makes more sense. Because now I can say exactly what kind of paths I'm trying to find. I'm trying to find the paths from my source to my sink using only the edges whose flow is smaller than their capacity, right? So if the flow on an edge is smaller than its capacity, I can use that edge to send some flow. And that includes this edge, this weird edge here, right? Because basically I can now send some flow from B to A. I can send 1 unit of flow from B to A, because that's equivalent to canceling the 1 unit of flow that I was previously sending from A to B. Okay. But I don't like this graph because this graph is too complicated. It's hard to work with this. Too many edges. If I want to find these paths several times, it gets really cumbersome. So I'm going to define another graph. And I'm going to call this the residual graph. So the residual graph of the flow F. And I'm going to show it with G sub F. Okay. This is a graph in which the weight of every edge is actually the difference between its capacity and its flow. Okay. So it's going to be a graph on the same set of vertices. So let me write it like this. GF has the same vertices as G. But then on every edge, I'm going to say how much of the capacity of this edge is remaining. And I show that with R. So R of UV is going to be the capacity between U and V minus the flow between U and V. Okay. Now, if I have this graph, I can just say whatever path that I find in this graph, and also I don't add the edges where the R is 0. So I say whatever path that I can find using non-zero edges in this graph is a path that can help me extend or augment my original flow. Okay. So let's do this again. So let's say this is my original graph. And I'm going to create a copy of it on this side. So this is my original graph. Let's call it G. And this is my residual graph, G sub F. And initially, I'm not sending any flow, so my residual graph is initially the same as my original graph. Okay. So what do? I find the path from the source to the sink in this residual graph. Okay. So let's say I find this path. Great. Now, what happens? First of all, how much can I send through this path? I can just take the minimum of the remaining values here, the remaining capacities here. So 1 unit. So I send 1 unit here. So I send 1 unit here. I'm sending 1 unit here and 1 unit here. Now, what happens to my residual graph when I do this? Okay. So this is what happens. First of all, I will change this edge. So I used to have a capacity of 5 from C to D, but now I have used 1 unit of that capacity, right? So the remaining capacity from C to D is only 4. But now I have a capacity of 1 from D to C, right? Because I can just cancel this 1 unit of flow that I sent from C to D. And here, the capacity from B to C was 1, but I used all of it. So I don't have any remaining capacity from B to C, so I lose the edge from B to C. But now I have an edge from C to B with capacity 1, with remaining capacity 1. And then here I had a capacity of 4 before. So now I'm going to have a smaller capacity. I'm going to have only a capacity of 3. And then I'm going to have a capacity of 1 in the other direction. Okay. So this is my new residual graph. Now, again, I do the same thing. In this new residual graph, I want to find another path from the source to the sink, and I want to use that path to increase my flow, to augment my flow. Okay, so I find another path. Let's say this time I'm starting here, so let's say I find this path. Okay, and I see that the minimum of the values here is minimum of 5 and 1 and 6, so I can send 1 unit of flow here. Okay. How does this change everything? Well, in my original graph, I'm sending 1 unit of flow here. Okay, so this is 1. And then I'm saying send 1 unit of flow up from C to D. So this just cancels the 1 unit that was sent from B to C before. Okay. And then I'm saying send 1 unit of flow from B to D. So I send 1 unit here. Okay. Now, what happens to my residual graph? I have to basically erase it and do it again because it's too much. So this is what happens here. I have my A, I have my B, C, and D, right? So from A to C, I have a remaining capacity of 4, but I can also send 1 unit back from C to A. From C to D, I have a remaining capacity of 4, but I can also send 1 unit back. From B to C, I have a remaining capacity of 1. From A to B, I have a remaining capacity of 3, but I can also send 1 unit back. From B to D, I have a remaining capacity of 5, but I can also send 1 unit back. So this is now my residual. Now, I'm really tired, so I'm not going to keep doing this. But basically, the idea is that as long as there is a path in my residual graph, I can get bigger and bigger flows, right? Because every time that I find the path here, so let's say, for example, I take this path. This adds 4 units to my flow if I just augment my flow using this path. Okay. And basically, by definition, whenever I find a path, it means that all the edges in my path had more capacity than flow. So I can push something on these edges. But when I'm pushing, I have to be careful. I have to say, well, sometimes I actually have this edge in the original graph, so I push more capacity in it. Sometimes I have the reverse edge, and there is already some flow, and I'm just canceling that flow. Okay, great. So every iteration of this algorithm is called an augmentation. So every time that I find a path in this residual graph, and I change the flow on that path in the original graph, that's called an augmentation. Okay. So now my algorithm for finding maximum flow is very simple. I say I start with a flow of 0, and I keep augmenting until I get stuck. When do I get stuck? I get stuck when in this residual graph GF, I cannot find any path from A to D. Actually, let me see if I can really get stuck here fast. So let's say that we augment this path. So I'm sending 4 units there. So this one will be 5. This one will be 5. And then I will lose this edge, and I will lose this edge. And I will have 5 here and 5 here, right? And then let's say next time I augment here with 3 units. So I will have 4 units of flow going here. And I will have 5 units of flow going here. And then in this one, I will not have this edge. I will only have the edge 4. And in this one, I will have both edges, but it's like I can have a capacity of 1 here and residual capacity of 5 in the other direction. And now finally, I don't have any path from A to D in my residual graph. So I got to a point where I can no longer augment my flow. Now, what is my flow here? It's 9. I can just take the sum of things that are going out of my source. Or I can take the sum of the things that are going into my sink. Why are they not the same? I did something wrong. Okay, yeah, this one should be 4 probably. Yeah, this one should be 4. I don't know how to add. This is 4. Okay, so fix this. This is 4. This is 4, this is 2. Okay. Great. Now I can't augment this anymore. But you know, when we were looking at matchings, we saw this difference between maximum and maximal matching. So we saw that we can have maximal matchings where I cannot add any edges anymore, but they're not necessarily maximum. So the question is, can I have a similar situation here? Maybe I start with an empty flow and I keep augmenting. And at some point, maybe I can no longer augment. But how do I know that that's the maximum possible flow? Maybe I just got stuck for some other reason. Maybe there is a different flow that can be obtained using a different algorithm and is more than what I have here. So the rest of this session is just about proving that this is not the case. Okay. By the way, this algorithm has a name. This is the Ford-Fulkerson algorithm. And basically, the idea is just this simple thing. So you create this graph, the residual graph. You keep finding paths in the residual graph, augmenting your flow, updating your residual graph, finding another path, and so on. Okay. Now, what I want to prove is that when this algorithm terminates, the flow that we have is an optimal flow. It's the maximum possible flow. Okay. So to do that, I have to define some notation. First of all, I want to kind of extend this function f that we had. So we have f of u and v right now, and u and v are just a pair of vertices. So this is like the flow from vertex u to vertex v. But I want to extend this to sets of vertices. So I want to be able to write something like this, f of a, b. Okay. And what I mean here is that I have two sets. I have a, and I also have b. I want to see how much water is flowing from A to B. Okay. But I can define this very simply. I can just say this is the sum over all A in A and the sum over all B in B of f of AB. Do you agree that this is the amount of water that is flowing from A to B? Because look, if I have some flow that is going from a vertex in A to a vertex in B, of course it's counted here. If I have some reverse flow that is going from somewhere in B back to somewhere in A, it's counted here as negative. So this is the net flow that is going from the set A of vertices to the set B of vertices. Okay. Now I want to prove some things about this. Well, first of all, what is f of SV? So here S is my source. So I mean the set containing only my source. And V is all of the vertices in my graph. So this is basically just saying what is the amount of flow that is going out of the source. And it can go anywhere, right? So this is going to be, again, the size of the flow, because this is by definition. This is like the sum of every V in V of F of SV, right? So similarly, if I ask what is the flow from everywhere to my sink? Again, this is the sum over all the vertices of the flow from that vertex to the sink. And by definition, this is the amount of flow that I have. Okay. But I can have some more interesting things. So let's say I have two sets, A and B. And let's say the intersection of A and B is empty. Okay. if this is the case, then what can I say about f of A union B and C? So I have three sets. So I have one set here, and I have two sets here. Okay. So I have A, B, and C. I'm saying what is the total flow from the union of A and B to C? And A and B are disjoint from each other. Okay. Yeah, so this is just the flow from A to C plus the flow from B to C. By the way, I'm only assuming that A and B are disjoint. In this picture, C is also disjoint from them, but this doesn't have to be the case. And again, you can prove this by just following the definition. So this was our definition. Just follow the definitions. Write the sums, they're the same thing. Okay. Great. So based on this, I can now define the notion of a cut. So here's what I say. I say a cut in my graph G is basically a division of the vertices of G into two parts. Is a division of vertices. So let's say I take my set of vertices and I divide them in two parts, A and B. And when I write like this, I mean disjoint union. So A and B don't have any intersection and their union is V. Okay, so I'm partitioning V into two sets such that my source is in A and my sink is in B. Okay. So whenever I talk about the cut in this session, later on we will have different definitions of cut for different problems. But here, whenever I talk of the cut, what I mean is that I've just randomly or arbitrarily divided the vertices into two sets. And my first set contains my source. My second set contains my sink. Okay. So let's say I have a cut. What is the flow from A to B if AB is a cut? Okay, so look at this. I have my set A here. I have my set B here. I have my source here. I have my sink here. I'm asking how much water is leaving A and going to B. Now, I know that for any node other than the source and the sink, the amount of water that is coming in is the same as the water that is going out, right? So the amount of water that is going from A to B is just the amount of water that is coming out of S and going into T, right? So F of AB, the flow from A to B, should again be the amount of my flow. Okay, I can prove this as well. What is the flow from A to B? How can I write this? I can say that this is the flow from A to all the vertices minus the flow from A to itself, because all of the vertices is just B union A. What is the flow from A to itself? 0. Again, you can prove that very easily, just use the definition, but this is 0. Okay. The flow from any set to itself is 0. Okay, so this is the flow from A to all the vertices. But I can break it like this now. I can say, well, A has two parts. I have the source and I have the rest of A. So this is the flow from the source to all the vertices plus the flow from the rest of A to all the vertices. Okay. And I claim this second one is also 0. Why is this 0? So let's say I have a bunch of vertices here. The vertices here are not T because T is in V. They're also not S because I'm saying look at A minus S. So for every vertex here, the sum of inflow is the same as the sum of outflow. So the flow from this vertex, from any vertex, let's call it, I don't know, A. The flow from any vertex A to all the other flows, sorry, to all the other vertices is 0, right? So F of AV is 0. This is just this one. Saying that for every vertex that is not source or target, the sum of the flow out of this vertex is 0. And this is exactly what F of AV is. So F of AV is 0. But then this one is just the sum of F of AV over all vertices A. So this one is also 0. But then this one is just the definition of my total flow, right? This is the flow from the source to all the other vertices. So what did I just prove? I proved that if I take a cut, the flow from the part that contains the source to the part that contains the sink is equal to my total amount of flow. Okay. Great. Now, here's another simple thing. If I look at the flow from A to B, this will be less than the capacity between A to B. And by the way, I'm defining this in the same way as well. So when I write C of AB, I just mean take the sum over all vertices in A and the sum over all vertices in B, the capacity from this vertex to that vertex. Okay. So the flow from A to B is less than or equal to the capacity from A to B, because you can just do definition chasing again. Right, the flow between any two vertices is less than or equal to the capacity between them. Okay, but this gives me a really nice way of finding upper bounds on the total amount of flow that I can set. Because what do I know? I know that this is my total amount of flow. So no matter what my flow is, my total amount of flow is going to be less than or equal to the capacity of every cut. So I can look at all the cuts, all the possible cuts, which are many, in my graph. I can find the capacity of every single one of them. And I know that my flow will always be less than or equal to every single one of these capacities. Okay. But one way I can prove my flow is optimal is if I find the cut where the capacity of this cut is exactly equal to the amount of my flow. Because for this particular cut, I know that every flow should be less than or equal to the capacity of this cut. And now I have a flow that is equal. So I cannot have more than this. Okay, so I want to find the cut whose capacity is exactly the amount of flow that I have. Okay, we go back here. Here's how I find my cut. I say, well, from A, or from my source, I cannot reach my target in my residual graph. So let's just see where I can reach. In this case, honestly, I cannot reach anywhere. I can just stay where I am. So I'm going to say my set A is the set of vertices that are reachable from my source in my residual graph. And I'm going to say that the rest of the vertices are B. And B is going to include my sink because I continued this algorithm until the sink was no longer reachable from the source, right? Okay, so here's what I do. I say when the algorithm is stuck, just define A as the set of all vertices reachable from the source in my residual graph. And let's say B is all the other vertices. Okay. Great. So let's say I have my residual graph here. I have my source. I have my set A. And then I have my set B. which contains my sink. Okay. First of all, I claim that in my residual graph, there is no edge going from A to B. Right? This is by definition. Because if I have an edge going from a vertex U here to a vertex V here, what was the definition of A? This was all the vertices that were reachable from S. So from S, I have a path to U. But then I can take this edge and I can reach V as well. So V should have been in A. So this shows that I don't have any edges between A and B in my residual graph. But what does this tell you about my original graph? So remember, my original graph G has the same set of vertices. So let's say this is my original graph, and this is my residual graph. My original graph has the same set of vertices as my residual graph, but it has different edges. Okay, so I might have an edge from A to B. I might have an edge from U to V here, and it has a capacity of UV, right? But this edge doesn't exist in my residual graph. What does that tell you? It tells you that the amount of flow that I sent here was exactly equal to the capacity, because I don't put the zero edges, and the definition of my residual graph was that the residual value on every edge is the capacity minus the flow. So if this edge exists here but doesn't exist here, it means that the flow on UV was equal to the capacity from U to V. Okay, fine. But can I have something like this? Can I have an edge that goes from this side to the other side? So let's call this, I don't know, alpha and beta. I'm really bad at naming. I can have this here as well, right? But the problem is, would I send anything here? Why not? Suppose that I was sending some flow here. Let's say I was sending 1 unit of flow here. What would that create in the other graph? So if I was sending 1 unit of flow here, it will create an edge in the opposite direction with 1 unit of flow. And I cannot have this, right? So every edge that I have from B to A in my original graph, it can have some capacity. I don't know what exactly its capacity is. It will have some capacity alpha beta, but the flow on this edge is definitely 0. Because if the flow is not 0, it will add an edge in the residual graph that I cannot have. Okay, so now what is the flow from A to B here? The flow from A to B is just the sum of every U in A, the sum of every V in B, the flow from U to V. But for these edges, I said that the flow was equal to the capacity. So instead of the flow, I can just write the capacity here. So this is the sum over U, the sum over V of the capacity of UV. But this is just the capacity from A to B. Okay. So when my algorithm stops, I have a flow F. And again, remember that this is equal to the total amount of flow. And my total amount of flow is equal to the capacity of a cut. But I said that for any flow, the total amount of flow would be less than or equal to the capacity of any cut. So the flow that I have here at the end of my algorithm has to be optimal, has to be maximum. Okay, great. But we also proved another thing. We proved that in any graph like this, the maximum flow is equal to the capacity, to the smallest capacity among all the cuts, right? Because this is a flow that is equal to the capacity of a cut. and every flow is less than or equal to the capacity of every cut. So if they become equal, it's the maximum flow, but it's also the minimum capacity cut. So this is called the max flow min cut theorem. Okay. But we have a problem. What is the problem? The problem is I said if this algorithm terminates, it will give you the optimal flow, right? But I was a little bit sketchy. I didn't prove that this algorithm terminates. Can this algorithm run forever? Well, it turns out the answer is yes. And you're going to Google it, and you're going to find an example where the algorithm runs forever. But the problem, and the reason this runs forever, is that we said our capacities are real numbers, right? So I'm going to start with a flow of 0, and every time that I'm augmenting it, my flow is going up. But if I'm working with real numbers, it can go up forever, right? So imagine that my flow starts at 0, and then it becomes 1/2, and then 1/2 plus 1/4, then 1/2 plus 1/4 plus 1/8, and so on, right? So my flow can increase forever. But here's where I cheat. Let's say that my capacities are natural numbers. If my capacities are natural numbers, then my flow, every time that it's increasing by at least 1 unit, right? And it cannot increase forever. There is a bound. So for example, the sum of all the capacities is a bound on the flow. You can never have a flow that is more than the sum of all the capacities. So every time that I'm augmenting my flow, the flow is increasing, and it cannot increase forever. So this algorithm terminates. But it only terminates if I say I have natural numbers. If I have real numbers, Google it, it doesn't terminate sometimes. Okay, and in 3711, you will see a very small edit to this algorithm that will actually make it terminate for real numbers as well.